Throughout history, philosophers and scientists have grappled with the fundamental question, what is light? Is it a stream of tiny particles that travel in straight lines and bounce off surfaces, like a hail of tiny cannonballs, as suggested by Sir Isaac Newton? Or is it a wave, like the sound waves or the familiar ripples on the surface of water? This debate, which has raged for centuries, was seemingly resolved in 1803 by Thomas Young's double-slit experiment. The beauty of this experiment is completely different behaviour expected for waves and particles. It finally looked like the argument could be resolved once and for all. This experiment is a cornerstone of understanding wave phenomena and early development of quantum theory. The experiment itself is deceptively simple. We only need a monochromatic, single colour light source, here a green laser pen, and an opaque barrier containing two very thin, closely spaced slits. We are going to shine the laser through the double slit aperture and observe the pattern produced on the screen behind it, by flipping the slits up into the beam. So what patterns do we predict? If light behaves purely as individual particles, they would travel in straight lines. They'd either pass through the left slit or the right slit, or bounce back when they hit the screen. We would expect to see two bright, distinct vertical lines corresponding to the light that made it through each opening. The rest of the screen would be dark. If light is a wave, as it passes through the two slits, a different phenomena occurs. Each slit acts as a new coherent source of light. This is due to diffraction, where the waves spread out after passing through a narrow aperture. As these two diffracted wavefronts spread, they overlap and interact, like dropping two identical stones simultaneously into a still pond. The resulting ripples meet and create a complex pattern. This interaction leads to interference. There's two types of interference. Constructive interference, when the peak crest of one wave meets the peak of another, or a trough meets a trough. Their amplitudes add together, resulting in a region of high intensity, a bright fringe. Or there's destructive interference. When the peak of one wave meets the trough of another, they cancel each other out, resulting in a region of zero or minimum intensity, a dark fringe. If light is a wave, we should see an interference pattern, a series of alternating bright and dark fringes, dots, spread horizontally across the screen, with the brightest fringe, the central maximum, directly opposite the midpoint between the two slits. As you can clearly see on the screen, the result is a long horizontal line of distinct bright and dark fringes. This unmistakable pattern of maxima and minima can only be explained by wave interference. The conclusion from Young's experiment was overwhelming. Light must be a wave. The spacing of the fringes allows us to calculate the wavelength of light if we wanted to, or in this case we could just look at the label on the laser. So light is a wave. Case closed? Well, not quite. About a century later, in 1905, Albert Einstein concluded that an experiment called the photoelectric effect, where electrons are emitted from a metal surface when light is shone onto it, could only be explained by assuming that light energy is delivered in defined packets of energy, which Einstein called light quanta, but were later named photons. This was a return to the particle view. So how can we reconcile this? The double slit experiment proves wave behaviour, while the photoelectric effect proves particle behaviour. Ultimately, we have come to describe light as both a wave and a particle, in a term called wave-particle duality. Light isn't either a wave or a particle. It exhibits both properties depending on the experiment being performed.